Sí. Desde luego ha sido una mañana bastante gratificante. Bueno, yo voy a hablaros de los... me ha dicho Raúl que la de en inglés, entonces voy a pasar a inglés, pero simplemente para que sepáis un cambio un poco de... Iba a hablar de una línea de investigación que llevamos desarrollando en el laboratorio en los últimos años sobre fibrosis hepática, pero he pensado que quizás también es bueno daros una imagen global, ¿no? de lo que hemos estado haciendo en el laboratorio desde que comencé mi grupo en el 2010, ¿vale? So I'm going to start with a simple question that I always keep in mind, and I'm sure that everyone that is working in some related issues with life science have at some point, and is how one single cell having a specific DNA component can give rise to different cell types, differentiate, specify to different cell types that is going to give rise to different organs and finally form a very complex organism. So as you might picture, this is controlled or regulated by multiple transcription factors and signaling pathways that we can imagine like musical notes that have to be in a very precise spatial and temporal pattern expressed and in a way that these musical notes are places in this pentagram to finally give rise to a complex and perfect song. So this is basically the germ of our research lines, try to understand how an organ is formed in order to understand how they function in the adult. So I'm a very defensor of developmental biology studies because visually every disease can be viewed as a failure in development. We also know that in some diseases like cancer, for instance, the cause if the reactivation of this developmental genetic program in a time where they're not supposed to. So if we learn how this genetic program works, we might learn how to shut them down when they're not required. And finally, of course, and this is something that has been really important in the last decade, thanks to developmental studies, developmental biology studies, we can now generate our cell of interest in a petri dish, just basically mimicking this developmental process that occur within the embryo. So now we can generate neurons, hepatocytes, cardiomyocytes, any kind of cell that is of our interest. So in our lab, we have been focusing to clinically relevant organs, the pancreas and the liver, how these organs are formed from the embryo, and we have used mouse models. So we know that dysfunction of these organs can lead to a variety of diseases, and I'm going to be focusing diabetes and cirrhosis. So as you might know, diabetes is a disease characterized for the high glucose levels in the bloodstream, and it's mainly due for the failure of beta cells. These beta cells produce insulin. Here you can see a histological section of a pancreas where you see the acinar cells that are the cells in charge to produce digestive enzymes. So the pancreas have two vital functions. One is generate these digestive enzymes, and the other one is the endocrine compartment here. These endocrine cells clustered in the islet or in the islets of Langerhans. So here you can see an immunofluorescence where the beta cells, the cells that produce insulin, are the majority within these islets. So I don't think that I have to convince you that how important is the study of diabetes, given the scary numbers that the scary data that the World Health Organization is telling us about the prevalence of this disease. So more than 400 million people are suffering of this disease. So these numbers are increasing. If you look like 30 years back, the population of diabetic patients have doubled in this time. So, and it's not a rich country problem anymore. So you can see even in Africa how the diabetic population have doubled. So according to the World Health Organization, in 2030, so it's like 10 years from now, diabetes is going to be the 6th cause of death. So having high glucose levels in your blood can lead to several complications like it's the leading cause of blindness in the adult. It's also the main cause of non-traumatic lower extremity amputations. It increases the risk of having a stroke or cardiovascular disease. And a long-term diabetic patient have renal failure. So you also know that there is the diabetes is presented in different ways. different forms, type 1 diabetic, which is an autoimmune disease, type 2 diabetic, which is the most prevalent cause. There's two conditions that coexist in these patients. There is failure of beta cells, but also insulin resistance, and also monogenic diabetes, which is caused by mutations in key genes for beta cell function. So as I say, we're interested in understanding how the pancreas is formed and how these beta cells are generated within the embryo, because we know that any defects in this process can lead to diabetes, whether this is a neonatal diabetes associated to pancreatic agenesis, I mean, the pancreatic organogenesis have been blocked, or whether there is a defects later in adult life of the beta cells. So we know already a lot about how the pancreas is formed, basically from mouse studies, because for obvious reason, human pancreatic development is limited, the studies are very limited. But this is the morphological changes that occur in the pancreas. The pancreas derived from the endoderm. The cells are specified by the activation of these 4 genes, which mark the pancreatic progenitor. So if we FAMAT these cells, they will give rise to the entire mature organ. And these progenitors start to proliferate and expand, and the pancreas acquire this ductal tree shape. This ductal tree shape in which the cells start to differentiate toward acinar cells or endocrine cells that we can see clusters in the adult pancreas. So as I say, there is a lot of transcription factor and signaling pathways that we know that are involved in these processes. Many of them, of course, are considered in human. And indeed, mutations, or a fair amount of these genes code for transcription factor, and mutation in this transcription factor lead to defects in either the organogenesis of the pancreas or the function of the beta cell. And here is a table in which I would like to highlight 2 transcription factors that have been recently added to this list, GATA4 and GATA6. This transcription factor is belong to a family, a very conserved family, from flies to human, and there is 6 members identified so far in mammals. They have been classified according to the function and the expression pattern. So there's the hematopoietic factors 1, 2, and 3, and GATA4 and 5 and 6 are transcription or genes that are expressed very early in development and also in the adult in different organs, in the heart, liver, intestine, testes. So these transcription factors are crucial for development because the standard knockout leads to embryonic lethality very early, just post-implantation. So we knew for a long time, our lab and others have shown that indeed GATA4 and GATA6 are expressed from the very beginning, even prior to pancreas specification, and they co-express through pancreas development. It's just in the pancreas, in the mature pancreas, where GATA4 is only expressed in the acinar cell, where GATA6 is expressed in the 3 pancreatic components. So even though we knew that they were expressed, and there was some human studies that were telling us that they were also expressed, there was no report related to the function of this transcription factor in human pancreas development or in mouse model. So if we look at the bibliography, what we see is that these genes are really cardiac genes. So there are several mutations that have been associated to congenital heart diseases. So tetralogy of Fallot, so disalignment of the outflow tract. So all these reports were indicating that these factors have an impact in cardiac morphogenesis. However, given the broad expression pattern of this transcription factor was kind of striking, why there's no more anomalies were associated or were reported in this patient. So it was in 2011 when a group of Andrew Hattersley in UK, where he did a whole exon sequence of children that were born without pancreas. So this is a very rare disease, and so far only have been associated to mutations in PTX or PTF1A, which are precursors of pancreatic progenitors. But as I say, there was only reports in a couple families. So the studies of Dr. Hattersley, where he says that indeed half of the patients carry mutations in GATA6. So this is the first time that these transcription factors were associated to pancreas organogenesis in humans. is the most prevalent cause of pancreatic agenesis. And of course, as expected, these patients or these children also have another anomalies associated to this, the expression of this gene. There is also a couple reports of GATA4 associated as well as neonatal diabetes with pancreatic agenesis. So in our lab, try to understand how this transcription factor work during pancreas development. We did some approaches in mouse model in which we inactivated these genes using a widely expressed pancreatic CRE line, PDX CRE line, that is expressed, as I say, in the pancreatic progenitors. And also we cross these mice with very standardized flux mice for GATA4 and GATA6. And when we cross these mice, what we observe is that here you have the viscera of mouse P1 neonate, where you can see the stomach, the spleen, the duodenum, and this whitish tissue is the pancreas. So what we observe is that when we individually inactivate GATA4 or GATA6, they don't have any major impact in the formation of the pancreas. That was unexpected because based on the human studies, in mouse, we couldn't be able to reproduce this data. So we will go to that controversial data somehow. But what we thought is that given the expression pattern, at least in mouse, where we know that these two transcription factors are co-expressed through pancreatic development, and they recognize the same sequence of the promoter of the target genes, this GATA sequence, that's why the name comes from, GATA motif. So we hypothesized that there might be a functional redundancy between these two transcription factors. And indeed, when we cross these mice and generate the double knockout for GATA4 and GATA6, these mice die a few hours after birth with a hyperglycemia due to the lack of this pancreatic tissue. So when somehow we recapitulate what happened in human. So again, to get further insight in how this transcription factor works, we went to different stages of pancreatic development, and when we observed is that by 13.5 in the mouse embryos, when the control mice already, this pancreatic epithelium are expanding and taking this ductal tree-shaped structure, in the double knockout, this pancreatic epithelium seems to be aberrant. So it's like a collapse, and they don't expand and they don't branch. So this is even more obvious at a little bit later when you see this nice ductal tree. And here in the double knockout, there's just a main duct, but not proliferation of the epithelia. So of course, in P1, there is only a main duct, but no signs of endocrine or exocrine cells. So we did more analysis of this double knockout pancreatic epithelium, and what we saw was that indeed there was a defect in proliferation. That's one of the reasons why this epithelium does not expand. There are also defects in differentiation. At this point of pancreatitis development, the cells start to be committed to acinar or endocrine cells, and when we look for markers for that, we did not see any proacinar expression marker here or endocrine marker. So the differentiation also was blocked. Of course, that was accompanied by the regulation of the multipotent pancreatic progenitors genes. But also what was interesting is that this pancreatic epithelium seems to be confused, and they even change fate, and somehow they acquire a hepatic fate. So they start expressing liver markers like albumin and different apolipoproteins. I have to say that pancreas and liver share many transcription factors, and indeed it has been thought that the ventral pancreas, which is the ventral portion of the pancreas, and the liver have a common precursor. So they have many transcription factors. It's very easy to convert a hepatocyte to a pancreatic cells and the other way around. So all this data here is telling us that GATA4 and GATA6 are at the top of the hierarchy, because even when we look at the mutants for these pancreatic progenitors that have the same phenotype, we place this transcription factor, as I say, at the top of the hierarchy. And in some cases, like the PDS, we have shown that it's a direct regulation through two conserved GATA sites that are in the PDX promoter. So as I said, the difference between mouse and human make us to think about if this is, where is the difference? So we have to keep in mind that we have used a CRE line using PDX CRE line. So that means that we have inactivated these genes once the pancreatic program have started. So that's different than what happened in human, which are being de novo probably in the germline. So that's one of the reasons. Another reason is that we don't know exactly at some point whether GATA4 and GATA6 in human pancreatic development already overlap as we see in mouse. But anyhow, in the human studies, it's very difficult to assess whether there is functional interaction between these two transcription factors. But two recent papers using IPS from patient carrying mutation in GATA6 or multipotent pancreatic, multipotent ES cells, in which have been modified by CRISPR-Cas to introduce GATA6 mutation, they have shown that indeed there is an interaction, a functional interaction between these two transcription factors when we use these cells to differentiate it toward beta insulin-producing cells. Here you see, for instance, when we compare the GATA dosage in this case, where you have the 2 copies for GATA4 and 1 copy from GATA6, you have some kind of impairment in the differentiation of these cells. But if you remove 1 allele of GATA6, this have a very more dramatic effect. So that's showing a functional interaction indeed in human differentiation. But one of the data that brought us our attention was that even when in the absence of 1 allele of GATA6, you produce beta cells, these beta cells were not completely functional. So that makes us to think that probably GATA6 also plays a role in the function of beta cells. Indeed, a couple of years before, the same group of, I mentioned before, Andrew Hattersley in UK, he did a more broadly study, and he showed that indeed there is some patients that have mutation in GATA6, and they don't have problem with the pancreatic development, so the pancreas is well formed, but this patient can develop diabetes in adult stages. So again, one more thing to think that maybe GATA6 is playing a role in beta cell function. So I told you when we inactivate individually GATA6, we didn't observe any defects in pancreas formation. And also at 2 months old, these mice are normoglycemic and they are glucose tolerant. However, when we did a follow-up of these mice, around 6 months of age, these mice developed glucose intolerance. And this glucose intolerance did not worsen, as you can see here, so it's maintaining along the time, but it doesn't get worsened. So more analysis of these mice, trying to explain this glucose intolerance, showed that indeed these mice have a defect in insulin biosynthesis, so they are not able to produce enough insulin, as you can see here by immunofluorescence, or quantify in isolate islets of the whole pancreas the amount of insulin within the islets. So you see here there is a decrease along the time, and by 6 months old, and other hormones are not affected, like glucagon here, but the insulin are much, much lower. But this is not the only reason, because when we check how this insulin, we have to keep in mind that the insulin that we produce, there's only around 2–3% of the insulin that is secreted in the media, so that can fully explain this glucose intolerance phenotype. But when we measure how these cells are able to secrete the insulin, and we did that by injecting glucose into the mice and then measure the insulin in the plasma, we see that indeed there is a decrease in the insulin secreted here in vivo or in isolate islets when they are cultured either, and this is important, either a basal level of glucose or high glucose. So it's not a defect in response to glucose, but also at a basal level. So the insulin transduction pathway is a common transduction pathway in which the glucose serves as a ligand, and inside the beta cell, the glucose is metabolized. There is some intracellular changes, like the closure of this potassium channel, the entrance of the calcium, which finally triggers the release of the insulin. So when we look at this beta cell deficient in GATA6 at the global level, what we saw is that indeed there was defects in many key components of this machinery. So there is a decrease in the glucose sensor, which sends the glucose to enter into the beta cell, in one of the subunits of the ATP-sensitive potassium channel. Of course, many transcription factors inside the beta cell that are also involved in the synthesis of the insulin, in the same transcription of the insulin. So this is just a transcription level. So all this data, just together, is telling us that this transcription factor play an important role, GATA4 and GATA6 play an important role in pancreas development by maintaining the proliferation, differentiation, and maintenance of the progenitor's identity. And GATA6 is an important regulator of glucose homeostasis because it controls the expression of key genes involved in biosynthesis of insulin and secretion of the insulin. One of the things that we are trying not to think is that why these mice never get diabetic, not even when they reach 1 year of age. So we have to keep in mind that we don't know if there is a compensatory mechanism. GATA6 is expressed, is something that we were thinking about. So GATA6 is expressed also in hepatocytes, so there might be a compensatory mechanism somehow from the liver part. These mice have been in a very equilibrated diet, so they hasn't been challenged. When we look at the mitochondria of this beta cell and the ER, they seem to be stressed indeed. So there is cellular stress. We still don't have any idea because, as I say, they don't develop diabetes. So what we are doing now is challenge them with a higher fat diet to see if we somehow can exacerbate the phenotype. Okay, so I'm gonna change now the organ and the disease, and I'm gonna be talking about some of the work that we have been doing regarding the molecular mechanism undergoing liver fibrosis. Well, you know that liver fibrosis induction is caused by different agents. It could be viral infection, alcohol consumption, steatosis, autoimmune disorders. These agents, these insults, can somehow induce inflammatory damage with a deposition of extracellular component of the matrix. The hepatocytes undergoes apoptosis. And this is just the early stages of fibrosis. But if the insult is still persistent along the time, the fibrosis can end to cirrhosis, in which there is already a uncompensated cirrhosis in which the patients cannot respond to the metabolic demand. The liver cannot respond to the metabolic demand because of this excessive accumulation of extracellular matrix that disrupt the liver architecture. So we know also that in advanced cirrhosis can lead also to hepatocarcinoma. But we also know that the liver have a huge potential of regenerative potential. So if we remove the agent that causing the damage, like for instance what happened with the antivirals for hepatitis C and B, these patients can somehow, the liver can regress and the extracellular component can be resolved and the liver can get to restore the function. So the liver, as the pancreas, is an endodermal organ. Indeed, as I say, is specified in a region adjacent to the pancreas. And here I show you how it is developed. In yellow is the endodermal part, the hepatocytes, and it's surrounded by endothelial cells and these mesenchyme cells. So the hepatocytes proliferate and invaginate into this mesenchyme. So in the adult livers, parenchymal and non-parenchymal cells are coexisting. So here you have the hepatocytes, which is the majority of the liver cells, around 85%. But we also have some other non-parenchymal cells, like endothelial cells, a special macrophage, the Kupffer cells, and these hepatic stellate cells that are originated, as I said, from this mesenchymal layer. So these hepatic stellate cells, usually in a normal liver, in a healthy liver, are quiescent, they don't proliferate. They storage vitamin A, and they represent around 5–8% of the total liver cells, so there's just a few of them. When there is an injury, these cells change the shape to a myofibroblast shape. They are contractile and they proliferative and they can migrate. And they start expressing smooth muscle alpha actin, which is a hallmark in liver fibrosis. these activate hepatic stellate cells are the major producers of extracellular component of the matrix, mainly collagen and laminin and probably lamica now. So I'll check definitely. So in the activation of the hepatic stellate cells, there is involved many paracrine autocrine pathways through different membrane receptors, nuclear receptors, head-chain ligands, and also some signaling from the innate immune system. So these cells have been of great interest in the field of liver fibrosis because we know that once the cell is activated, if we remove the damage, these cells can either undergo apoptosis or revert to an inactivated state. And this is crucial for the liver fibrosis to regress. So we need these cells become again inactive, start to produce collagen, so there is a resolution of this extracellular components, and then the hepatocytes have first space and also the positive induction signaling to proliferate and repopulate the damaged tissue. So we know that, and indeed, in the mouse studies, the lineage tracing have shown that when we label these cells and we mimic a damage in vitro, these activate cells, when you remove the damage, only a small population undergo apoptosis, but the majority indeed regress to this inactive state. These cells are more prone to respond to a second damage, so somehow they keep the memory of the damage. So GATA4 is expressed also in these hepatic stellate cells, but only in this liver cell type. As you can see here, in mouse and human, the expression of GATA4 is restricted to this hepatic stellate cell, but not in the hepatocyte. We even know how this transcription factor is expressed there, or how it's regulated, the gene is regulated in this specific cell type. I told you at the beginning that GATA4 is expressed in pancreas, in liver, in heart, in testes, intestine. So how this gene is regulated in so many different cell types. So this is part of the work that I was doing when I was in San Francisco during my postdoc, is try to figure out how it's regulated. So GATA4 gene is really a long gene, it's almost 100 kb. And what we found is just conserved region among different species, non-coding region, that were, as I say, very conserved. So we assume that this region have been conserved through evolution because they are important, so they might represent regulatory sequence. And indeed, when we did transgenic analysis by cloning of these enhancers with a Laxi reporter, we found that indeed each of them direct expression in different cell types. So here you have the cardiac enhancer, specifically the second heart field, or you have here the pancreas and liver. We also identify another enhancer that is only restricted to the dorsal pancreas but not the ventral. But I want you to keep in mind about this enhancer called G2, which is around 40 kb upstream of the transcriptional initiation site. So as you can see here, the expression pattern of this enhancer is basically in the mesenchyme cells that surround the liver. In a closer view of this enhancer, you can see here the specific expression in the mesenchyme component, but not in the endodermal. This is going to be the future hepatocytes, and later in development, again. And in a cross-section of this liver, you can see this mesenchymal part and the hepatic stellate cell that are originating for the delamination of these mesenchyme cells into the space of the disc. That's where the hepatic stellate cells are located in the liver. So we generate a CRE line using this G2 sequence, and we were able to efficiently label more than 85% of the hepatic stellate cells. So at the beginning, our interest was try to understand how GATA4 contribute in this hepatic stellate cell to liver formation. So we wondered whether if we inactivate GATA4 in this mesenchymal component of the liver, how the liver is going to be affected, in the organogenesis. Because there was several studies that were doing with mosaic GATA4 or with other kind of approaches that couldn't definitely define an autonomous role for GATA4 in liver development. So that was our main goal. And indeed, when we generate the knockouts, the first thing that we saw is that they were embryonic lethal. So these are the genotypes. The genotype is that we get from the cross, and we didn't get any newborn mine. So actually, we are losing the Mendelian region around 13.5, so the embryos are dying approximately around this age. So this is the aspect of the knockout mice, the knockout embryo at 13.5. You already can see that this embryo is kind of a pale, and if you look at the liver here, compared with the control or the isolated liver, you see that this liver is hypoplastic, and even with some lobules that look like fibrotic lobes. So the embryonic lethality of the mice, we were wondering, because at this point of the development, the liver still don't have any metabolic function. But we have to keep in mind that the liver is our hematopoietic organ during development. So one of the reasons that, or at least what we thought that these embryos, the lethality was caused, was because the hematopoietic niche as a secondary defect was affected. So the disruption of this liver were enabling to the hematopoietic niche to expand. Indeed, when we look at hematopoietic progenitors, they were decreased. But when we look at the liver of these embryos, what we found is indeed there is an activation of the hepatic stellate cell. This is expressing smooth muscle alpha actin, as I told you, is the hallmark of the liver fibrosis. And indeed, there was accumulation of different collagen, and here I show you collagen 4, but there is a different type of collagen and laminin. And in this data is like the normal expression pattern that we see in a liver fibrosis that occur in adults, caused by different agents, as I said before. So all this data, what it's telling us is that GATA4 is maintaining the quiescent stage of the hepatic stellate cell. So if we remove GATA4, this hepatic stellate cell gets active, and they start producing extracellular component of the matrix, and therefore inducing the fibrosis. That was really nice, but still these embryos, because the lethality, we couldn't do any studies in adults. There is no inducible Cre line that allow us to inactivate this gene in adult hepatic stellate cell. But we have done some approach to see whether this role of GATA4 in the maintenance of hepatic stellate cell quiescent is conserved also in adult. And we really think that, I'm going to show you one of the approaches that we follow. Indeed, one of them was the haploinsufficiency, to see if one dosage of GATA4 is more prominent to develop liver fibrosis in carbon tetrachloride model. And indeed it was. But the other one was, we use flox mice in which we inject adenovirus expressing the Cre recombinase or the GFP as a control. So the injection through the vein tail has certain tropism to the liver, so that was good for us. And indeed, what you see here is that when we injected these mice with GFP, there was no induction of fibrosis. Here is Sirius red, collagen fibers. However, when we inject with the Cre recombinase, there was a excessive accumulation of the hepatic stellate cells, or the accumulation of collagen, and here activation of hepatic stellate cell by the small muscle alpha actin marker, in cells that were not expressing GATA4, as you can see here. So it seems that this mechanism, or this role of GATA4 in keeping this hepatic stellate cell quiet, is also conserved in adult. So, of course, we wanted to go further and see how is evaluate the GATA4 expression in human liver biopsies of patients with different etiologies of liver fibrosis and different degrees. So these are samples of F0, F1. F0 means like it's a normal healthy liver. F1 is a very, very light fibrosis, and that goes from F0 to F4, which is already cirrhotic liver. So we staining with Sirius red just to check the accumulation of collagen. And we see here that in F0 patients and F1 patients, we still see a nice GATA4 expression. However, as the disease progresses, and we see a major accumulation of collagen here, we start losing GATA4 expression. So there is an inverse correlation of GATA4 expression with the degree of the disease, and also at the transcriptional level. So with all this data that we just published a few years ago, we're still trying to think whether what happened in a liver patient, in a liver fibrotic patient, if we are able, or patient, in this case, a mouse model, that's what we're doing, hopefully in some point in human. But what happens if we are able to restore the GATA4 expression in a cirrhotic hepatic stellate cell? So are we able to revert this phenotype? So we know for the animal model I showed you, human biopsies, that the quiescent cells start activated. So can we restore the GATA? What happens if we restore the GATA4 expression in these activated cells? Are they undergoing apoptosis, or are we able to revert the phenotype and therefore regress the fibrosis? So in order to do that, what we did is we use a human-derived hepatic stellate cell line, LX2, which have been generated by Scott Friedman. And these cells are already active, as you can see here. They express all the markers, fibrotic markers. So we overexpress GATA4 in these cells, and that was very appealing because what you see here, the cells that have been, and this is a different concentration of a virus, the cells that are overexpressing GATA4, they start losing, in this case we use the laminin, they start decreasing the fibrotic marker. So at a global level, again, we wanted to see how different is this, the gene profile of these cells compared with this one. So what is GATA4 doing in these cells to revert the phenotype, the active phenotype? So an analysis, what we show in this analysis is that indeed that we're confirming the reversion of the phenotype. So there is a down-regulation of fibrotic gene, an upregulation of some anti-fibrotic genes. So definitely the overexpression of GATA4 in these activated hepatic stellate cells are reverting the phenotype. So in order, again, to get more detail, we try to identify direct target of GATA. I saw you it's a transcription factor, so they might be modulating directly some of the genes. So we did also a ChIP-seq and combined the data from the gene expression data and the ChIP-seq. And we found 35 genes, 50 of them upregulated and 19 of them downregulated. So we are still working in these genes, in these targets, but it's one of the genes that I didn't show you here. One of the genes that can also draw our attention is that the hypoxia-inducible factor 2A was downregulated. So this factor, hypoxia-inducible factor, they are normally post-translational regulated. So they are basically with a expression, a constant or a constitutive transcription, but they are regulated post-translational. So that was kind of surprising. However, in the ChIP sequence, we can find that indeed GATA4 is binding to a conserved region, to 2 GATA sites in the conserved region of this gene, meaning that GATA4 somehow is repressing the transcription of the genes. This is kind of a novel, and I'm not sure at what point we're being able to convince the people, because this is just something that we didn't expect. And of course, we also find as a positive control, and we knew that the GATA4 is auto-regulated through this enhancer. So as I said, the hypoxia-inducible factor is regulated post-translationally. So in normoxia, these proline residues are hydroxylated, and then they are degraded by the proteasome. However, in hypoxia conditions, these proline are not hydroxylated, and the HIF can go translocate into the nucleus and activate the target genes. So there is some studies of hypoxia-inducible factor in liver fibrosis with HIF-1 alpha and HIF-2 alpha, but they are only done in the context of the hepatocytes. So that was also kind of a new, trying to understand what these transcription factors are doing in this hepatic stellate cell. So to figure out what they are doing, we use a mouse model in which, basically this is a mouse model in which we can stabilize the protein, the HIF2 protein, so they not degrade, and they are always translocated to the nucleus. So there's a gain of function for HIF2 alpha. So when we did this, indeed, we observe as well a phenocopy of what we see in the GATA4. I have to say it's not as dramatic as the GATA4, so for sure this is not going to explain the whole picture, but what we observe is that, again, there is an activation of hepatic stellate cells and accumulation of extracellular component of the matrix. So somehow that can be at least part of the explanation why GATA4, the inactivation of GATA4 leads to liver fibrosis in the mouse model that we had before. So with all this, at the end, we are working in a in vitro cell culture, and we are reverting the phenotype, but the ultimate goal is to revert or regress the fibrosis. So we wanted to know whether the modulation of this hepatic stellate cell by GATA4 was sufficient to regress the liver fibrosis, at least in the mouse model. And to do that, what we did is we use a widely used liver fibrosis model, the injection of carbon tetrachloride, different injections to get a moderate fibrosis. And after that, we inject the mice with GATA4 or GFP as a control, directly by the vein tail. So what we see here, this is a mice injected with a vehicle, olive oil, and this is Sirius red just around the vessel, the blood vessel. And this is the induction of the carbon tetrachloride. So you can see already here the accumulation and the deep breaches of the collagen fiber. We also wanted to control that the adenovirus injection, the GATA4 adenovirus injection per se does not induce the liver fibrosis, and we didn't observe any induction of the fibrosis. So in these mice, once we have generated the liver fibrosis, when we inject with adenovirus GFP, we'll still see accumulation of collagen. However, this is a dramatic decrease that we observe when we inject these mice with adenovirus overexpressing GATA4, and this is the quantification of the collagen area. Here you see again smooth muscle alpha activation, so there is a decrease in activated hepatic stellate cell, which explains the liver regression. So what we are doing now is, again, one more time, is that, okay, how can we restore the GATA4 expression in a patient with liver fibrosis? So having this sequence identified is going to be, or it's going to make us a little bit easier to find compounds, soluble compounds that can restore GATA4 expression specifically through this sequence without touching the expression of GATA4 in heart or pancreas or other tissues. And that's something that we are doing now. We are generating a stable cell line with this construct in which the GFP is directed by the G2 activity enhancer. And this, we are doing a stable line here, with a stable line with the LX2 cells. Of course, because they are active, this reporter is going to be off. And what we expect is that when we have the construct, it's going to be an easy way to screen compound libraries that are G2 responsive. And of course, we are aware that we can find all kinds of cells, right? We can find cells that are expressing GATA4, and therefore they may revert the fibrosis. Probably some of them are also unable to revert the fibrosis, or but anyhow, I think within that could be definitely a good tool to start screening for compounds that. So as a conclusion, we have shown that in mouse model, GATA4 maintains the quiescent state of hepatic stellate cells, not only in the embryonic stages, but also in the adult. We have shown that in vivo, GATA4 is able to revert the phenotype of the hepatic stellate cell and regress liver fibrosis, at least in the CCL4 model. We are also trying a different model for liver fibrosis to see if this is also conserved. And as a future, close future, depending funding, depending people, depending more, is the urgent needs to find soluble agents aiming to restore the GATA4 expression. And also something that is now very trendy is try to modulate or to reverse or to inhibit the progression of hepatocarcinoma just by modulation of the hepatic stellate cells. So now we think that we have at least one of the tools to modify this hepatic stellate cell, and we want to see whether we are able to change the phenotype of hepatocarcinoma cells. With all this, I would like to thank the people that really made this work. Manuel and Irene did all the embryonic part of the pancreas, the first part that we did. Laura and Elisa have been very helpful. Laura is indeed did all the work for the beta cell function. Elisa and Alberto have been also involved in this paper, in the diabetes paper. And Laura have been definitely the most productive, because all the liver stuff that I told you have been done by her as for her thesis. She will defend in a couple of months. Collaborators from CABIMER, Benoit and Francisco Martín, from the Universidad Miguel Hernández, Iván, Paola Martinelli from Vienna, and Lorenzo Pasquali, who helped us with the bioinformatics, which we are definitely lack of ideas with bioinformatics. So thank you very much.
Muchas gracias, Anabel. Mi pregunta se basa en si se conoce el papel que tiene GATA4 más allá de la fibrosis, en estadios más tardíos, por ejemplo, de la enfermedad hepática. Me explico, porque me gustaría saber qué papel podría tener terapéutico GATA4, por ejemplo, en cáncer de hígado, y qué sentido tendría. Porque, como tú sabes, la mayoría de las células cancerígenas podría revertir se podría desdiferenciar el papel de estas células y tener un papel más como el papel que tendría su origen embrionario. En sentido de la expresión de GATA4 en un comienzo, sería un papel diferente al que nos encontramos con la fibrosis a nivel terapéutico. No sé en qué sentido.
Pues sí, tienes razón. De hecho, hay estudios que han visto que en la progresión del hepatocarcinoma en pacientes que llevan mutaciones en GATA4, de hecho es una delección del gen, pues en esos pacientes el hepatocarcinoma es mucho más agresivo. Y eso tiene su sentido porque GATA4 se expresa en los estadios primarios de los hepatoblastos, es decir, es necesario para la diferenciación de los hepatocitos. Pero después, una vez que el hepatocito está maduro, su expresión se extingue. Entonces, claro, en una situación de diferenciación, como tú dices, si no tienes GATA4 que pueda, de nuevo, diferenciar esas células hepatocitos, puedes estar induciendo, ¿no? Lo que decíamos antes, induciendo o agravando, ¿no?, el hepatocarcinoma, permitiendo la progresión. En ese sentido, GATA4 tendría un papel, claro, obviamente distinto al de las estrelladas. Claro. Bueno, la idea mía, o la idea que tenemos en el grupo es intentar ver cómo la modificación del fenotipo de las células estrelladas, por GATA4 en este caso, cómo esas células modificadas por GATA4 que señalizan al hepatocarcinoma, ¿vale?, para proveer. O sea, no es GATA4 per se, pero sí encontrar factores solubles o rutas de señalización de esas células estrelladas moduladas para evitar la progresión del hepatocarcinoma. Pero sí tienes razón, sería un papel distinto.
Siguiente pregunta. Primero quería felicitarte porque la verdad que he disfrutado mucho de tu trabajo. Y quería hacerte una pregunta, a lo mejor un poquillo flipadilla, pero preguntarte si conoces si la región G2, esta específica de tu célula de interés, está muy lejana a la zona que controla la expresión de GATA4. Porque sabes que en medicina el tema de introducir genes, cortar tal, y eso está muy mal visto. Está lejos de utilizarse, pero quizás utilizar para ese tipo de experimentos, utilizar un sistema CRISPR-Cas que no corte, sino que lleve acoplado factores de transcripción de GATA4 para inducirlo, a lo mejor sería una aproximación más sana o más cercana a la medicina, quizás.
Pero repíteme, o sea, seguro que es muy interesante, pero es que me he perdido. O sea, hacer un CRISPR-Cas para llevar...
Claro, el CRISPR-Cas tú lo puedes dirigir a tu zona G2, que es específica de tus células de interés, ¿no? La región G2 es una secuencia específica de las células...
Bueno, la región G2 está en todos lados, lo que pasa es que es activa específicamente en las células estrelladas.
Activa, pero está presente en la secuencia en las demás zonas.
Claro.
Ah, pues entonces, no sirve...
Es ADN, al final, todo, claro.
Vale, pues felicidades por tu trabajo.
Muy bien.
En primer lugar, muchas gracias por la charla, ha sido muy ilustrativa, muy estimulante. Yo tenía ganas de saber algo más de Gata 4, Gata 6, pero siempre falta tiempo para leer. Y al hilo un poco de la pregunta de Juanlu, pero retrotrayéndome a la primera parte de tu charla, me pregunto cuál es el posible papel, si se conoce, si se ha estudiado de Gata 4, Gata 6, en las células madre del cáncer, en las células madre del cáncer pancreático específicamente. Un estado quiescente de células madre, pero células madres malas, entre comillas, donde hay un proceso de desdiferenciación y de reposo. Y no sé si se ha mirado, evidentemente es un compartimento celular muy pequeñito, Emi puede dar buena fe de ello, y quizás sería interesante interrogar esas células sobre el papel de Gata 4 o Gata 6.
Pues en células madres pancreáticas, que yo sepa, también a mí me falta tiempo para leer, pero que yo sepa, no he visto nada. Obviamente estos factores sí están implicados en cáncer pancreático, sí, como sabes por los trabajos de Paco Real, pero en las células madres no lo sé.
Gracias.
Bueno, yo tengo una pregunta. ¿Alguien más? ¿Alguna otra pregunta? Bueno, yo, Anabel, gracias por la presentación, sobre todo muy didáctica también. Entonces, yo tengo una pregunta respecto, que ya la habíamos comentado. ¿Sabes que hay isoformas de splicing del Gata 4? Y acabo de ver en el PubMed que se han visto en un paper reciente relacionadas con la enfermedad cardíaca congénita, o sea, que están directamente implicadas en esa enfermedad. Viendo lo que tú has hecho del chipsec y modulando la expresión del Gata 4, que has dicho que se autorregula su expresión, ¿habéis mirado o tenéis pensado? O sea, sería algo muy interesante mirar si la modificación del Gata 4 modifica la expresión de las variantes de splicing y si tiene algo que ver la expresión con el empeoramiento de la enfermedad hepática en este caso o incluso de la reversión. Es decir, no sé si tenéis pensado, si has leído algo, si habéis estudiado...
No, de hecho, por lo que estoy aquí, para hablar contigo de eso, no. Hombre, estos estudios son de pérdida de función. Yo no sé, estaría encantada de ver qué pasa en esas estrelladas si hay también una desregulación de...
Que de hecho la diabetes, claro. O sea, que la charla ha sido muy... Porque se me han encendido un montón de bombillas porque la diabetes, hay una reversión de diabetes, se ha visto asociada, la hemos visto asociada a cambios en la maquinaria de splicing, de factores de splicing, y creo que por aquí podrían ir a lo mejor los tiros, es decir, que sería muy interesante.
O sea, quiero decir... Cuando yo he mostrado las biopsias de humanos en los que se apaga la expresión de Gata 4, obviamente estos humanos no son knockouts para Gata 4. No sabemos qué está señalizando a Gata 4 para que se apague. Pues a lo mejor, no sé, uno de los mecanismos puede ser eso, a través de regulación del esplesiosoma. Sería genial.
Bueno, pues ya tenemos una colaboración.
Muy bonita charla en los dos temas diferentes y estupendos, la verdad. Una cosa, en el caso del hígado, ¿Gata 6 hace algo?
Gata 6 se expresa también en hepatocitos, a diferencia de Gata 4. Y nosotros no hemos visto, hemos visto expresión en las estrelladas también, porque además se expresa también en las pancreáticas, en las estrelladas pancreáticas de Gata 6, y algo que también estamos empezando a mirar. Pero en activación con esta línea específica de estrelladas no produce fibrosis.
O sea que no es redundante en ese caso con la función. ¿Y interaccionan las estrelladas con macrófagos? Sí, ¿no? Es que tiene más pinta de...
es un crosstalk entre hepatocitos, macrófagos, endoteliales y las estrelladas. O sea, ahí...
Es que tiene pinta. Muy bonito.
¿Y el factor de transcripción Gata, sabes si se secreta?
Ojalá, porque, vamos, Cuando nosotros estuvimos viendo la disminución en la expresión de la fibrosis en pacientes, dijimos, anda, un biomarcador. Y hay un par de papers por ahí, pero bueno, cuestionables, en los que hablas que en enfermedades cardiovasculares habían intentado detectar niveles de GATA4 dependiendo de distintas enfermedades cardiovasculares en exosomas. Nosotros lo hemos intentado, hemos cogido células blancas, hemos intentado ver GATA4, date cuenta que aquí lo que estábamos buscando es ver una disminución, en principio, bueno, también puede haber un aumento, ¿no? Por si se secretan más, no lo sé, pero fuimos incapaces.
¿Pero por algo técnico o porque creéis que no...?
Probablemente algo técnico, probablemente es algo que dejamos abandonado porque fue difícil conseguir esas muestras. Y probablemente por algo técnico, pues simplemente aislar exosomas de una muestra pequeña de células blancas no es trivial, pero es algo que, claro, que no, bueno, esto fue patentado en su momento como biomarcador, aunque fuese en biopsia no invasiva, pero bueno, la patente como todas, pues tuvo sus 3 años de gloria y ya está enterrada. Pero sí es verdad que quisimos verla, usarlo a ver si como biomarcador en plasma, que hubiese sido genial. Y nunca lo llegamos a, digamos, a abordar, ¿no? De forma esto, pero prácticamente por falta de más material, ¿no?
Pues muchísimas gracias, Anabel.
Nada, vosotros.